Chapter 1. The beginning of the cosmic clock, the Big Bang and the birth of time. Friends of knowledge, observers of the limits of the observable, prepare yourselves. What you are about to experience is not a simple journey through time. It is a cosmic explosion in your perception of reality itself. Since consciousness first flickered on this small blue dot, we have looked up at the stars and asked not only how everything began, but how it will end. Is the universe eternal, an endless cycle, or is it moving inexorably toward a final dissolution? A cosmic silence, a tearing scream, or perhaps an unexpected rebirth? Modern science, from the primordial echoes of the Big Bang to the enigmatic whisper of dark energy, speaks to us in truths that challenge even our boldest imagination about the ultimate fate of everything that exists. If you are ready for your vision of the cosmos to fracture and be rebuilt, if you are willing to challenge every certainty, then join us on this expedition. And if at the end of this astonishing journey, you feel your soul vibrate with truth, I invite you to join the Quantum Observer community. Your subscription is not just a click. It is a passport to continue exploring the deepest secrets of the cosmos with us. Prepare yourselves. From this moment on, the universe will never look the same again. You are here, right now, at a tiny point within a vast and ever-expanding universe. You feel the ticking of time, the relentless march of seconds, minutes, and days. You look toward the stars and see the light of galaxies stretching across billions of light years. But have you ever stopped to think about the true origin of all this? Not only of matter and energy, but of space itself, and of the most enigmatic dimension of all, time. Prepare yourselves, because we are about to travel back to the primordial instant, to the Big Bang, not merely as an event, but as the birth of the cosmic clock. The moment when existence itself began its great narrative. For millennia, humanity wrestled with the idea of an eternal universe, without beginning or end. Ancient civilizations imagined endless cycles of creation and destruction, or gods that had always existed. Newtonian science presented a static universe, a giant clock that had always been running. But the 20th century brought one of the most profound and counterintuitive revelations ever conceived. The universe had a beginning. Not a beginning in time, but the beginning of time itself. Imagine a point of infinite density, of unimaginable temperature, hotter and denser than the core of any star, a place where the laws of physics as we know them break down. This incomprehensible singularity is the canvas from which everything that exists emerged approximately 14 billion years ago. It was not an explosion in space, it was the explosion of space itself, and with space, time was born. Before the Big Bang, according to most modern cosmological theories, the concept of before has no meaning. There was no pre-Big Bang, because there was no time for it to exist within. Time did not pre-exist the universe. Time, along with the three spatial dimensions, emerged from that primordial singularity. It was moment zero, the first vibration, the first bit of information, the first instance of change that set the cosmic clock in motion. The evidence for the Big Bang's the foundation of modern cosmology, supported by unshakable observational pillars. In those earliest moments, the universe was unimaginably small and dense, so dense that the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have been unified into a single superforce. As the universe expanded at breathtaking speed, it cooled, allowing these forces to separate. Elementary particles, quarks and leptons, formed from a sea of energy. It was a boiling, primordial soup where matter and antimatter constantly annihilated each other, leaving behind a slight excess of matter, an imbalance that would form everything we see today. First, the expansion of the universe. In the 1920s, Edwin Hubble discovered that galaxies are moving away from one another at speeds proportional to their distance. This was proof that the universe is expanding, and if it is expanding, then in the past, it must have been smaller and denser. Second, the cosmic microwave background. This is the echo of the Big Bang, the residual glow of the universe's first light, released about 380,000 years after the beginning, when the universe cooled enough for atoms to form and photons to travel freely. It surrounds us completely, at a temperature of 2.7 Kelvin. Its tiny fluctuations are the seeds of every star and galaxy we see today, the fingerprint of the universe's youth, the stuttering whisper of time at its birth. Third, the abundance of light elements. The observed proportions of hydrogen, helium, and lithium match precisely the predictions of Big Bang nucleosynthesis during the first minutes after the beginning. Fourth, tiny fluctuations, cosmic consequences. The minute temperature variations in the cosmic microwave background became the seeds of large-scale structures, galaxies and galaxy clusters. Gravity amplified these irregularities, shaping the vast cosmic web we observe today. The Big Bang was not just the birth of matter. It was the birth of the arrow of time. Before that instant, there was neither order nor disorder, because there was nothing to be ordered. As the universe expanded and cooled, it evolved from a state of extremely low entropy to one of increasing disorder. This is the second law of thermodynamics operating on a cosmic scale, the engine that drives time forward from the first breath of existence toward its possible end. For you, for me, for every conscious being that has ever existed. The Big Bang is moment zero, the beginning of our shared story. It is the origin of the temporal illusion that allows us to experience cause and effect. Without that primordial imbalance, there would be no past to remember and no future to anticipate. Thus, the Big Bang is the story of time itself, the spark that ignited the cosmic clock, the instant when existence began to unfold into a vast and astonishing narrative. And by understanding this majestic beginning, this birth of time, we prepare ourselves for the rest of the journey. To understand how this initial expansion carries us inexorably toward a destiny, toward a possible end that still looms as the greatest mystery of all. Chapter 2. The Revelation of Expansion, Hubble and the Universe in Motion. In the 1920s, an astronomer named Edwin Hubble, with the patience of a craftsman and the vision of a prophet, began to uncover a truth that would shake the foundations of cosmology. Hubble demonstrated that the spiral nebulae seen in the sky were not clouds of gas within our own galaxy, but vast and distant galaxies, entire islands of stars beyond the Milky Way. This was the first step, the revelation that the universe was far larger than we had ever imagined. Most humans throughout history grew up believing in an essentially static universe. Stars moved in their orbits. Planets danced around their suns, but the cosmic backdrop itself seemed eternal and unchanging. Even Albert Einstein, in his early formulations of relativity, introduced a cosmological constant to force the universe to remain static, a belief so deeply rooted that it resisted being broken. But reality proved far more dynamic and far more mysterious. The true turning point came when Hubble combined his observations with the work of Henrietta Leavitt on Cepheid variable stars, stars whose pulsating brightness reveals their intrinsic luminosity, allowing precise distance measurements. With this tool, Hubble calculated the distances to faraway galaxies with unprecedented accuracy. At the same time, he analyzed the light coming from those galaxies. And this is where physics revealed its magic. When a light-emitting object moves away from us, its light waves stretch, shifting toward the red end of the spectrum. This is known as redshift, the cosmic equivalent of the Doppler effect. Hubble observed that nearly all galaxies showed redshift. They were all moving away from us, but the revelation went even deeper. The farther a galaxy was, the greater its redshift, meaning it was receding faster. This became known as Hubble's law. A galaxy's recession velocity is directly proportional to its distance from us. The implications were monumental. If the universe is expanding, then in the past it must have been smaller, denser, and hotter. Rewind the cosmic expansion far enough, and you reach a point of infinite density, the Big Bang. Hubble's discovery did more than confirm the universe's birth. It gave us the first clue about its dynamics and its possible fate. Cosmology was transformed. Newton's static, eternal universe was replaced by a dynamic cosmos with a past, a present, and, crucially, an uncertain future. The question, does the universe have an end, was no longer philosophical. It became a scientific problem, one that could be studied through physics and observation. This did not mean Earth or the Milky Way was at the center. It meant that space itself is expanding. Imagine inflating a balloon with dots drawn on its surface. As it expands, all dots move away from each other. The farther apart they are, the faster they seem to separate. Galaxies are not moving through space. Space itself is stretching between them. Hubble showed us that the universe is in motion and laid the groundwork for understanding the forces that drive, slow, or accelerate that expansion. The image of an expanding universe places us not in a static stage, but aboard a cosmic vessel, moving away from its origin toward an unknown destination. And the key to that destiny would come from one of the greatest mysteries ever discovered. Chapter 3. The Dark Queen of Destiny. Dark Energy and Cosmic Acceleration. At the end of the 1990s, the universe delivered a shock that defied all expectations. Two independent teams studying Type Ia supernovae, stellar explosions used as cosmic distance markers, made a stunning discovery. The universe was not just expanding, its expansion was accelerating. If gravity were the only force at work, the expansion should be slowing down over time, so gravity should act like Earth slowing a ball thrown upward. For decades, the question was whether expansion would eventually stop and reverse into a big crunch, or slow forever without stopping. But instead, the universe was behaving as if an invisible force was pushing it outward faster and faster. Distant galaxies were receding more rapidly than expected, at an increasing rate. This implied the existence of an unknown energy exerting a repulsive pressure, pushing space apart rather than pulling it together. This mysterious entity was named Dark Energy. Dark energy is by far the most abundant and enigmatic component of our universe, making up approximately 68% of the total cosmic energy density. And with its discovery, the fate of the universe became more mysterious than ever before. To put this into perspective, ordinary matter, stars, planets, galaxies, you and me, accounts for only a negligible 5% of the universe. Dark matter, that invisible mass exerting attractive gravity, makes up about 27%. The rest, the overwhelming majority of the cosmos, is dark energy. It is the true dark queen of cosmic destiny, the force that dictates the future of everything that exists. The cosmological constant. The simplest idea is that dark energy is a cosmological constant, the same one Einstein introduced and later regretted as his greatest mistake, to keep the universe static. The concept now, reinterpreted, it would be a form of energy inherent to space itself, a negative pressure that does not dilute as the universe expands. It is the energy of the vacuum itself, a fundamental property of space-time. But what is dark energy? The truth is, we do not know for certain. It is the greatest mystery of modern cosmology. We have several hypotheses. 1. Quintessence. Another possibility is that dark energy is a new type of dynamic energy field, quintessence that varies over time and space. If this is the case, its properties could change in the future, leading to even stranger cosmic destinies. 2. Modified gravity. Some theorists suggest that dark energy does not exist at all, but that Einstein's general relativity must be modified on cosmic scales. In this view, gravity behaves differently at the largest distances, explaining the acceleration without invoking a new form of energy. Whatever its nature, dark energy is the dominant force shaping the fate of the universe. Its repulsive pressure is pushing galaxies farther and farther apart at an accelerating rate. This has catastrophic consequences for any scenario involving a cosmic collapse. Dark energy is, in essence, winning the battle against gravity. The most direct implication is that the universe is heading toward a future of eternal expansion and increasing isolation. Galaxies will slip beyond our observable horizon. The universe will cool inexorably. Matter and energy will thin until they are nearly zero. This is a future of desolation and silence, a cosmic heat death. Dark energy is the engine driving us toward that cold and lonely end. This discovery marked a total paradigm shift. We moved from a universe that might collapse or expand slowly to one accelerating toward emptiness and darkness. It is a humbling and awe-inspiring truth, revealing that most of the cosmos is governed by something we cannot see, touch, or fully understand. Dark energy is the loudest echo of how mysterious the universe truly is. It is the invisible force writing the final chapter of cosmic history, pushing galaxies toward oblivion and matter toward dissolution. By understanding the reign of this dark queen, we come one step closer to envisioning the most probable fate of everything that exists. A future of stillness, absolute cold, where entropy reaches its ultimate expression. Chapter 4. Heat Death, the most likely end of the cosmos. You are accustomed to a vibrant universe, shining stars, rotating galaxies, life pulsing with energy. But if dark energy continues its reign, the destiny of this universe is an ending that defies imagination through its passivity and its immense time scale. This is the heat death, also known as the Big Freeze or the Great Silence, the most likely end of the cosmos. Imagine the universe as a clock set in motion, the Big Bang wound it up with energy. The current expansion, accelerated by dark energy, is like hands spinning faster and faster. But this constant expansion has a fundamental consequence. It dilutes matter and energy, disperses heat, and drives the universe inexorably toward maximum entropy, a state of thermal equilibrium where no energy gradients exist and no work can be done. Cosmic eras. 1. The stellar era, now to 100 trillion years. You live in the stellar era. Stars are still born from clouds of gas and dust. They shine brilliantly and die in spectacular supernovae. Galaxies like the Milky Way and Andromeda remain gravitationally bound, and some will collide. But this era is finite. As gas and dust are depleted, star formation will slow and eventually cease. Massive stars burn fast and die first. Red dwarfs, small and long-lived, will shine for trillions of years, but even they will fade. 2. The degenerate era, 100 trillion to 1 quadrillion years. Once all stars exhaust their fuel, the universe will grow far darker. Stellar remnants will dominate: white dwarfs, neutron stars, and black holes. Planets, stripped of starlight, will wander, frozen through darkness. Gravitational interactions will eject many remnants into intergalactic space. 3. The black hole era, on 1 quadrillion to 10 to 100 years. The universe becomes a vast cosmic graveyard. Ordinary matter grows increasingly rare. Only black holes remain, but even they are not eternal. Stephen Hawking predicted that black holes emit radiation and slowly evaporate. A solar mass black hole would take trillions upon trillions of years to disappear. A supermassive black hole would take a time written as a 1 followed by 100 zeros, beyond comprehension. As black holes evaporate, the last matter dissolves into elementary particles and low-energy photons. 4. The Dark Era, after 10 to 100 years. The universe reaches maximum entropy. No stars, no galaxies, no black holes. Only a cold, dark void remains, filled with a thin soup of photons, neutrinos, and perhaps electrons and positrons. Temperature approaches absolute zero. Change ceases. The arrow of time effectively stops. The illusion of time dissolves into an eternal, unchanging present. Chapter 5. The Big Crunch. Could the universe reverse course? Contemplating this probable end is not meant to depress us, but to inspire awe. It reminds us how precious the stellar era is. A brief window where light, life, and consciousness are possible. But is heat-death the only possible ending? Imagine a universe with a different density of matter and energy, one where gravity ultimately wins. In that universe, expansion would slow, stop, and reverse. Space itself would begin to contract. This is the Big Crunch. Galaxies would rush together. Collisions would become inevitable. Radiation would compress and reheat. Atoms would be crushed, matter returning to a primordial plasma. The universe would collapse into an infinitely dense, hot singularity, the inverse of the Big Bang. Some theories suggest this could lead to a big bounce, a rebirth. A new universe emerging from the ashes of the old, like a cosmic phoenix. However, current observations of dark energy make this scenario increasingly unlikely. The cosmic ball was thrown too fast, and an anti-gravitational force is pushing it even faster. Yet the idea of a cyclic universe remains one of the most profound and hopeful visions science has ever imagined. Chapter 6. The Great Tearing, when darkness rips reality itself apart. Although the Big Crunch is considered less likely based on current evidence, studying it remains vital. It forces us to consider that the universe may be far more dynamic and complex than it appears at first glance. It invites us to reflect on the delicate balance between expansion and contraction, between creation and destruction. It reminds us that the fate of the universe is a dance between matter, energy, and mysterious forces operating on cosmic scales. And as we contemplate that fiery ending, we prepare ourselves for an even more dramatic scenario, one born from dark energy itself, a fate not of compression, but of tearing reality apart. You have seen the possible destinies of the universe, from the stillness of heat death to the crushing collapse of the Big Crunch. But if dark energy truly rules cosmic destiny, what if its nature is even more extreme than we imagine? What if this repulsive force does not merely accelerate the expansion of space, but becomes so powerful that it overwhelms all other fundamental forces, ripping matter apart at every level until the universe itself disintegrates into subatomic fragments? This is the most violent and terrifying scenario for the end of the cosmos, the Big Rip. If dark energy were a form of phantom energy, its repulsive power would grow without bound, progressively overpowering all other forces of nature within a finite amount of time. The timeline of this cosmic apocalypse would unfold as follows. The Big Rip scenario arises if dark energy is not a cosmological constant, but an even more powerful form of energy, often called phantom energy. This energy would have a unique and devastating property. Its energy density would increase as the universe expands, rather than remaining constant or diluting. Imagine a force that not only pushes, but becomes stronger the more it pushes. That is phantom energy. To understand the Big Rip, we must look deeper into the nature of dark energy. The simplest hypothesis, the cosmological constant, assumes that dark energy's density remains constant throughout space as the universe expands. But what if dark energy is a more dynamic entity, one with even more exotic properties? The sequence of cosmic disintegration. 1. Galactic tearing. Billions of years before the rip. The repulsive force of phantom energy would first overcome the weak gravitational bonds holding galaxy clusters together. Individual galaxies, such as the Milky Way and Andromeda, would cease to be gravitationally bound and begin drifting apart at ever-increasing speeds. The night sky, seen from within a galaxy, would grow progressively darker as other galaxies vanished beyond the observable horizon. 2. Stellar system disintegration. Millions of years before the rip. As phantom energy grows stronger, it would overpower the gravity-binding individual galaxies. Stars and planetary systems would be torn from their galaxies and scattered into the vast cosmic void. Planets like Earth would be ripped from their orbits, and rogue stars would wander aimlessly. Galaxies would dissolve into clouds of dispersed starlight. 3. Planetary system destruction. Month before the rip. In the final months before the Big Rip, phantom energy would become strong enough to overcome the gravitational forces binding planets to stars and moons to planets. The solar system would disintegrate. Earth, if it still existed, would be flung away from the sun. Planets would lose their moons. For the tearing of matter. Minutes before the rip, moments before the end. The repulsive force of phantom energy would overwhelm electromagnetic forces, the forces that hold atoms and molecules together. Planets, stars, neutron stars, and even black holes would be literally torn apart. Molecules would split into atoms, atoms into nuclei and electrons. 5. Atomic and subatomic disintegration. The moment of the rip. In the final instant, phantom energy would overpower the strong and weak nuclear forces, the forces that bind atomic nuclei and subatomic particles like quarks. Atoms would dissolve into their most fundamental constituents. The entire universe would become a diffuse soup of elementary particles flying apart at infinite speed in a space expanding at an incomprehensible rate. This is the Big Rip, the most absolute and violent ending imaginable. There is no cold, uniform remnant as in heat death, and no return to a primordial point as in the Big Crunch. Space and time themselves are torn apart as distances between particles become infinite in a finite time. Information, the substance of time itself, would disperse beyond all possibility of recovery. The likelihood of the Big Rip depends critically on the nature of dark energy. If its energy density increases with expansion, this is our fate. However, current observations, while confirming the existence of dark energy, are not precise enough to determine whether it is strictly constant or phantom in nature. Most current data favor a cosmological constant, making the Big Rip less likely than heat death, or pushing it so far into the future that it becomes effectively unobservable. Still, contemplating the Big Rip is deeply unsettling. It forces us to confront the fragility of all structure, even the atoms that compose us. It reminds us that the universe possesses unimaginable power, capable of unleashing forces far beyond human intuition. Dark energy, the queen of our destiny, may not only push us forward, but tear us apart in the darkness. Chapter 7. Ghosts of the Vacuum. Disintegration of ordinary matter. You are made of matter. Your body, the air you breathe, the ground beneath your feet, the stars above, all are composed of atoms. At the heart of those atoms lie protons and neutrons, particles we consider stable, immutable, the pillars of existence. But if the universe is heading toward an end, what happens to these fundamental building blocks of reality? Are they truly eternal, or do they too have an expiration date on the vast cosmic calendar? Prepare yourselves, because we are about to explore the ultimate fate of ordinary matter. a scenario in which even protons fade into the vacuum. In the physics we know, the proton, the particle that defines elements and forms atomic nuclei, is considered stable. If it were unstable, matter as we know it would fall apart instantly. However, some of the most advanced theories in particle physics, especially grand unified theories, GOTs, predict that the proton is not eternally stable. They predict that the proton decays. Imagine a future so unimaginably distant that all stars have gone dark, galaxies have dispersed into blackness, and only cold stellar remnants remain. In that era of desolation, matter itself would face its final fate. If protons decay, they would do so with an incredibly long half-life, far exceeding the current age of the universe. Estimates suggest proton lifetimes of at least 1034 years, possibly 1038 years. For perspective, the universe today is only about 14 billion years old, 1.4x 1010 years. The probability of a single proton decaying is minuscule, but over unimaginable timescales, it is not zero. How would a proton decay? Theories suggest it could transform into lighter particles, such as a positron, the electron's antiparticle, and a neutral pion, which would quickly decay into photons and neutrinos. Matter would slowly melt away, a gradual unraveling of the pillars of existence. Consequences of proton decay: dissolution of stellar remnants. White dwarfs and neutron stars would slowly decay into clouds of lighter particles. The end of chemistry. Without protons, atoms cannot exist. No molecules, no elements. Chemistry itself would end. The disappearance of planets, moons, and asteroids would slowly dissolve into subatomic particles, then into light and neutrinos. A universe of ghosts. The cosmos would be dominated by electrons, positrons, neutrinos, and photons, ghostly remnants drifting through expanding space. Proton decay remains hypothetical. Experiments like Super Kamiokande in Japan actively search for it, but none has been detected so far. This does not rule it out. It merely implies that proton lifetimes are even longer than initially predicted. Yet the very possibility forces us to confront a future in which even the matter of our own bodies is not eternal. Chapter 8. Twilight of the Titans, the evaporation of black holes. You know black holes, cosmic devourers, points of no return, where gravity is so extreme that not even light can escape. They are the densest objects in the universe, the final fate of massive stars. They are often imagined as eternal prisons. But reality is more astonishing. Even black holes are not eternal. In the 1970s, Stephen Hawking made a revolutionary discovery. By applying quantum mechanics to black holes, he showed that they are not completely black. They emit radiation. This Hawking radiation causes black holes to lose mass and, over vast timescales, to evaporate completely. Near the event horizon, particle-antiparticle pairs constantly appear from the quantum vacuum. Occasionally, one particle falls into the black hole while the other escapes. The escaping particle carries energy away, energy stolen from the black hole itself. Over time, an incomprehensibly long time, even the greatest cosmic titans fade into nothingness. The rate at which a black hole emits Hawking radiation and loses mass is inversely proportional to its size. Smaller black holes evaporate faster, while larger ones do so more slowly. And when we say slowly, we are speaking of timescales that defy human imagination. A black hole with the mass of the Sun, a relatively small stellar black hole, would take approximately 1067 years, a 1 followed by 67 zeros, to evaporate completely. To put that into perspective, the current age of the universe is only about 14 billion years, or 1.4 is 1010 years. This means that even the smallest stellar black holes formed in the early universe have barely begun to evaporate. A supermassive black hole like the one at the center of our galaxy, Sagittarius AI, with a mass of around 4 million suns, would take far longer, approximately 200 years, a 1 followed by 100 zeros. This number is so vast that it lies beyond human comprehension, a timescale that dwarfs all other cosmic measures. The implications of black hole evaporation are profound for the final fate of the universe, especially in the heat-death scenario. First, contribution to entropy. Hawking radiation is a process in which the information of a black hole, everything that fell into it, is gradually dispersed into the universe as thermal radiation, increasing the total entropy of the cosmos. Black holes, which seem to swallow entropy, in reality release it slowly, contributing to the universe's maximum entropy state. Second, the end of extreme density. After the degenerate era, when the universe is filled with stellar remnants, the evaporation of black holes means that even the most concentrated and dense forms of matter dissolve. The final strongholds of gravity fade away. Third, a truly empty universe. Once all black holes have evaporated and protons have decayed, if proton decay is correct, the universe will be almost completely devoid of matter. What remains will be an extremely dilute soup of low-energy photons, neutrinos, and electron-positron pairs, scattered across an accelerating expansion. As we contemplate the slow agony and fading of black holes, we glimpse a future so distant it borders on abstraction. A time when the universe sheds its grandest structures and becomes a frozen whisper. It is the final act in the great play of entropy, leaving behind a cosmos where the light of suns is only a memory and darkness reigns supreme. But if all visible matter disintegrates and black holes evaporate, what happens to light itself? Does the glow of existence vanish entirely? Chapter 9. The Last Breath of Light. Ghost photons and final darkness. The twilight of the Titans shows us that nothing in the universe is truly eternal, except perhaps space-time itself. Even the most indestructible objects, those gravitational monsters that challenge our imagination, have finite lives and obey the laws of quantum thermodynamics. You live in a universe bathed in light, sunlight that fills your days, moonlight that softens the night, and the glow of billions of stars forming the Milky Way. Light is the primary messenger of cosmic information, the invisible thread that weaves the fabric of observable reality. But if the universe continues to expand, and does so at an accelerated rate driven by dark energy, what happens to light as eons pass and the cosmos thins into emptiness? Prepare yourselves, because we are about to explore a future in which light takes its final breath and the universe sinks into permanent, irreversible darkness. Consider the phenomenon of redshift, discovered by Edwin Hubble. When a source of light moves away from you, its light waves stretch, shifting toward the red end of the spectrum. The faster the source recedes, the greater the redshift. Now imagine this effect on a cosmic scale over billions upon billions of years. As the universe expands, galaxies drift apart. Photons, the particles of light traveling through space, are literally stretched by the expansion of space itself. As a photon's wavelength increases, its energy decreases. In a universe heading toward heat death, this expansion continues forever and accelerates due to dark energy. The consequences for light are devastating. First, cooling of cosmic radiation. The light from the Big Bang, the cosmic microwave background, currently at 2.7 Kelvin, will continue to stretch and cool. Its wavelength will grow enormous, its energy infinitesimal, becoming practically undetectable. A faint cosmic radiostatic, or even less. Second, disappearance of galaxies beyond the horizon. As expansion accelerates, distant galaxies will recede faster and faster. Eventually, They will move away so rapidly that the light they emit will never reach us. They will vanish beyond our cosmological event horizon, the limit of what we can observe. The night sky will grow progressively darker as galaxies disappear one by one, like ships slipping beyond the horizon of an infinite sea. Third, the extinction of stars. As we've seen, stars have finite lifespans. The massive ones will be long gone, and even red dwarfs, the longest-lived stars, will fade after trillions of years. No new stars will form. The universe will become a place of final and eternal darkness. Thermal radiation will be so cold and diffuse that the concept of temperature will nearly lose meaning. Matter will have disintegrated or diluted into invisibility. What remains will be a vast, frozen, silent void, crossed only by the last, stretched, energyless ghost photons that once illuminated a vibrant universe. Fourth, ghost photons. Even photons from the final stars and evaporating black holes will fall victim to expansion. Their wavelengths will stretch to unimaginable lengths, their energies reduced to near zero. They will still exist, but so diluted, so powerless, that they will be practically undetectable. They will illuminate nothing, carry no useful information, mere echoes of a light that once was. This darkness is not the absence of light. It is the extreme dilution of light itself, stretched and cooled into insignificance by the relentless expansion of space. To contemplate this final breath of light is to meditate on the fleeting nature of visible existence. The era of light is only a chapter in a far longer and ultimately darker cosmic story. Chapter 10. Cosmic Loneliness, the Vanishing of Galaxies Beyond the Horizon. You live in a vibrant universe filled with galaxies. The Milky Way is one among billions. Each galaxy, spiral or elliptical, is a majestic collection of stars, gas, and dust. They cluster into groups, clusters into superclusters, forming a vast cosmic web. But if dark energy continues accelerating the expansion of the universe, this interconnection is temporary. We are heading toward an era of overwhelming cosmic loneliness, where most of the universe vanishes forever beyond our observable horizon. Galaxies move apart, not because they travel through space, but because space itself stretches. And this stretching accelerates. Like dots on the surface of an inflating balloon, they drift farther apart. Inflate the balloon fast enough, and some dots recede so quickly that light from them can never reach you. This will happen to all galaxies beyond our local group. Our small cluster, including the Milky Way, Andromeda, and a few dozen smaller galaxies, remains gravitationally bound. In about 4.5 billion years, the Milky Way and Andromeda will merge into a new giant galaxy, often called Milkomeda. Beyond this island, darkness will dominate. Future civilizations, if consciousness still exists, will see only their own galaxy. All others will have faded into eternal darkness. The universe will become a lonely island of light in an infinite sea of nothingness. Chapter 13. A universe without consciousness. The death of the cosmic observer. Right now, you are living proof of consciousness in the universe. Your thoughts, emotions, and awareness illuminate reality itself. But if the cosmos is moving toward an end, whether heat death, the Big Rip, or vacuum decay, what happens to consciousness? Is it as fragile as matter, or does it possess a resilience that allows it to transcend the death of stars and galaxies? Modern science largely views consciousness as an emergent property of the brain, a result of billions of interconnected neurons and their complex electrochemical dance. If this is true, then the fate of consciousness is inseparable from the fate of matter and energy. Consider the end-of-universe scenarios. First, heat death. In this future of eternal expansion and absolute cold, the universe becomes a place of maximum entropy, with no energy gradients capable of sustaining work organization, or biological consciousness. Biological brains require a temperate environment and a constant source of chemical and thermal energy. In a universe approaching absolute zero, brains would freeze and cease all activity. Consciousness, as we know it, would fade out. Artificial consciousness. Computers, even the most advanced ones, also require energy and a low-entropy environment to process information. As the universe grows colder and more diffuse, the available energy needed to keep computers running would decrease dramatically. Computational operations would slow to infinitesimal rates and eventually stop altogether. Artificial consciousness, if it is ever achieved, would also meet its end. The Big Rip. This is the most catastrophic scenario for consciousness. If phantom energy tears apart atoms themselves, there would be no material structure capable of sustaining consciousness, biological or artificial. The mind would disintegrate along with the matter that composes it. It is an absolute end for the observer, where reality itself is torn apart and the possibility of perception is erased. Vacuum decay. If the universe collapses into a true vacuum and the laws of physics change dramatically, the particles that form our brains, or any conscious substrate, could transform or cease to interact in the way that sustains consciousness. The identity of the mind would dissolve into a new reality governed by unknown rules. This raises the terrifying prospect of a universe without observers, a cosmos that, after billions of years of evolution, of the emergence of life and consciousness, sinks into an existence where there is no one left to witness its vast darkness, its final stillness, or its violent dissolution. The cosmic drama would reach its conclusion on an empty stage. But what if consciousness is not merely a product of the brain? What if it is something more fundamental, something capable of transcending matter? This question takes us to the very limits of science and philosophy. Consciousness as a fundamental property. If panpsychism is correct, and consciousness is an inherent property of matter at a basic level, or even of space-time itself, then consciousness might persist in some rudimentary form, even in a diluted universe. However, it would not be the complex, organized consciousness we experience, reincarnated or reconstructed consciousness. Some theorists, speculating beyond current science, propose that the information of consciousness might be preserved and perhaps reconstructed in a future universe, in a cyclic scenario or in an extremely low-energy state. But this drifts into the realm of science fiction and metaphysics. The final cosmic mind. Others speculate that consciousness might not vanish, but instead unify. As energy sources dwindle, advanced civilizations could merge their minds into a massive collective consciousness, a cosmic mind that, operating at an extraordinarily slow pace and using the final embers of energy or even vacuum energy itself, would become the last observer of a dying universe. This mind could be so vast and slow that its experience of time would stretch across eons, contemplating eternity within a single moment. The idea of a universe without consciousness is deeply unsettling for many. It suggests that purpose, meaning, beauty, and wonder are temporary, that they exist only as long as there is a mind to perceive them. Without observers, the universe simply exists without being known or experienced. Yet at the same time, this contemplation can be a powerful catalyst for appreciation. If consciousness is finite, if our ability to observe is limited, then every moment we have to witness this vibrant universe becomes infinitely precious. It urges us to explore, to understand, and to marvel while we still have light to see and minds to comprehend. The end of the universe, if it includes the death of the observer, is the culmination of the great cosmic narrative, the moment when the drama ends and the theater empties. It forces us to confront the fragility of our existence and the immensity of what lies beyond our understanding. And yet, even in contemplating a universe without consciousness, consciousness itself persists long enough to bear witness to its own existence. It is a paradox, a final echo suggesting that even in dissolution, the act of questioning and observing may be the deepest truth of all. Is the end a new beginning? Is this fate part of an eternal cycle? Only time, or its absence, will tell. Chapter 14. The Eternal Cycle. A new beginning after the end. You have witnessed the most dramatic scenarios for the end of the universe. Heat death in its frozen stillness, the Big Rip in its cosmic violence, the unstable vacuum rewriting reality, and the melancholic fate of consciousness. Each of these endings seems to seal the fate of the cosmos with a sense of irreversibility. But what if cosmic history is not a straight line toward a final point, but a circle? A wheel turning endlessly through eons of existence? What if the death of one universe is, in fact, the birth of another? Welcome to the fascinating and highly speculative theory of a cyclic universe. The idea of a cyclic universe is not new. Ancient philosophers and cultures already envisioned cycles of creation and destruction. In modern science, this idea gained momentum with the possibility of the Big Crunch, which we explored earlier. If the universe contained enough matter and energy for gravity to overcome expansion, it would collapse back into a singular state of infinite density and temperature, similar to the Big Bang. The bold question that follows is inevitable. Could that singularity be the Big Bang of a new universe? Not an end, but a rebound. The Big Bounce. Imagine the universe as a vast cosmic spring. It stretches outward from a tiny point. The Big Bang expands for billions of years, reaches a maximum extension, and then contracts under its own gravity, returning to a point of infinite density. But instead of collapsing into nothingness, the universe bounces, erupting into a new Big Bang and beginning a fresh cycle of expansion. The implications of a cyclic universe are monumental. Infinite time with no beginning or end. In a cyclic universe, time has no true origin and no final conclusion. Cycles follow one another endlessly, an eternal sequence of cosmic births and deaths. The Big Bang would not be an absolute beginning, but the rebound of a previous universe, resolving the mystery of what came before it. Variation between cycles. Each cycle could be slightly different. The laws of physics, fundamental constants, the amount of matter or the nature of dark energy might vary from one cycle to the next. Every universe would be unique, yet born from the ashes of the previous one. A cosmic phoenix endlessly renewing itself. Entropy and the cycle. The second law of thermodynamics states that entropy always increases. How does this fit into a cyclic universe? Some models suggest entropy is reset at each bounce, or that each cycle grows slightly larger or more entropic than the last. Other, more sophisticated theories propose that entropy is conserved or even reduced at the bounce through quantum processes we do not yet understand. Cyclic models have gained renewed interest through loop quantum gravity and certain versions of string theory, which aim to unify general relativity with quantum mechanics. In some of these models, the Big Bang is not a singularity but a transition, a bounce from a contracting universe. There is no infinite collapse, only a moment of maximum density followed by renewed expansion. However, current observations of dark energy and accelerated expansion present a major challenge. Dark energy appears to drive the universe toward eternal expansion, preventing the contraction needed for a bounce. For a cyclic universe to work, dark energy would have to disappear, change its nature, or unknown properties of matter would have to force contraction. At present, there is no evidence for this. Despite these challenges, the cyclic universe remains deeply appealing. It offers a vision in which the end is not final, but a transformation, a rebirth. It allows us to imagine that life and consciousness might arise again in future cycles, in new galaxies, in an endless cosmic dance. To contemplate the eternal cycle is to meditate on the resilience of the universe. Creation and destruction are not opposites, but two sides of the same coin, parts of an infinite cosmic ballet. It reminds us that while our individual lives and even our universe may be finite, existence itself could be immortal, an unending flow of births and deaths on a scale beyond comprehension. This is the final great question about the end of the universe. If there is an end, is it truly an end, or merely a pause before a new and glorious beginning? The answer, if we ever find it, will redefine not only our cosmic destiny, but the very meaning of existence, the value of time, and the purpose of life in a universe that may be, at its deepest level, an endless poem.